Good morning, Year 12. So, this video is just going to go through question number 1 in the June 2017 paper. So you should, as I've said before, just, go through the paper, watch the video, and then answer the questions as it goes along. So, I'll give you some tips, you can have a go at the questions, then you can check your answers, see how you're doing, and then carry on, rather than if you just watch the video straight through, it won't be very interesting. If you want to just try the paper without the video, that's fine, but the paper will give you, the video will give you lots of hints and tips. Okay, so we've got a bit of stuff about potassium permanganate. Nice bit of introduction about this pink tap water that they had in this Canadian town. Right, so section 1, write down the electron configuration of manganese in terms of its subshells. All right, so that's fairly straightforward. Manganese is here in the periodic table, so I think you should be able to write that down. And the graph on the right shows the first 10 successive ionization energies of manganese. All right, so this is the kind of graph that you should be used to from my classes. So we have the successive ionization energy number along the bottom, and then how much energy there is, and obviously it's going to increase because you know that the more electrons you take off, the more energy you need to do that. Suggest the highest oxidation state that manganese can exhibit in its chemistry. So obviously there's something in this graph that should give you a hint as to what the highest oxidation state is. Now obviously manganese is a metal, so it's going to lose electrons. So what is the maximum number of electrons it can lose? All right, and you can justify your answer using that graph. I don't think that should be too much of a problem. Potassium permanganate contains the MnO4- oxyanion, in which there are covalent bonds between manganese and oxygen. Draw a dot and cross diagram to illustrate the bonding in the manganese O4- ion, showing only the electrons in the outer shells of the atoms involved. So I think you should be able to have a good stab at this. MnO4-. Now you've worked out the oxidation number. So that's going to give you a clue as to how many electrons are involved in bonding. All right, so you can imagine, if at this point you should have worked out the oxidation number. The highest oxidation number is 7. Okay, so we can just assume that it's 7. Now that means that there's going to be 7 electrons of manganese involved in the bonding, and you've got a central manganese atom, and you've got 4 surrounding oxygen atoms. All right, so I think you can start off by perhaps having your manganese in the middle and then your oxygen atoms around the outside, and then think to yourself, well, if I've got 7 manganese electrons, right, how are they likely to arrange themselves? All right, so perhaps I'd have 1 manganese, 2 manganese, 3 manganese, 4 manganese. So I've used 4 of my manganese electrons. How are the other 3 going to get used? Okay, so it could be that there's going to be a lot of lone pair electrons, or it could be that I'm perhaps going to have some double bonds. All right, so that might be your oxygen electrons. Okay, but you obviously need to fill in the rest of the electrons from there. And then once you've got a structure, you should be able to suggest a bond angle for that. And also remember, when you're doing this, because it's a minus, you're always going to have an extra electron in there. So if you're ever short of an electron somewhere, you don't forget that you've got that negative charge, which is going to add an extra electron in. All right. So next, write a balanced equation for this reaction. So we've got KMnO4 is produced industrially from the mineral pyrolusite, I think, a naturally occurring source of manganese 4 oxide. In the first step, of KMnO4 production, it is heated with potassium hydroxide in the presence of air, okay, producing potassium manganate and one other product. All right, so what we've got is we've got a reaction where our product is going to be heated with potassium hydroxide. So I'm heating KOH in the presence of air. All right, so that's probably going to be something, there's going to be something in air that reacts here, producing potassium manganate 6. and one other product. All right, so there are things that I need to work out. Okay, so I need to have here my potassium manganate 6. I've got my other product. Okay, here I've got something from air, and over here I've got my pyrolusite, or however you pronounce it. Okay, and this is a common kind of question they like to ask, where they want you to write out an equation, but you sort of need to work out from the information in the question what the things actually are. Okay, so now remember, pyrolusite is a source of manganese 4 oxide. So this is actually manganese 4 oxide. Okay, so this thing here, potassium manganate, is going to have potassium in it, it's going to have manganese in it, and it's going to have oxygen in it. And the manganese is going to be in the oxidation state +6. This naturally occurring source of manganese 4 oxide, that's going to have manganese and oxygen, with manganese in the oxidation state 4. All right, so what you should be able to do now is you could, from this information, you know that this is manganese in the +4 oxidation state and oxygen. You should work out what the formula of that is. You know that you've got potassium, manganese 6 and oxygen. You can work out what the formula of that is. Okay, remember that, you know, it's going to be a salt, so potassium is +1, so then whatever you've got here is going to have an overall oxidation state of -1. All right, now if you can't make that work, remember you can have more than one potassium. All right, and then you should be able to balance it. I think it's probably going to be pretty obvious what the thing from air is going to be. All right, and then that should let you work out what the other thing is. So when you have a go at that one, and then once you had a go at it, check the answer for that before you move on. All right, that's quite a good little problem to work through. Right, so next. All right, the potassium manganate 6 is then dissolved in a solution of potassium hydroxide and converted into potassium manganate 7 by a process known as electrolytic oxidation. In this process, water is reduced to hydrogen gas. Remembering that the reduction is the gain of electrons, write an ionic half equation for the reduction of water to hydrogen gas and hydroxide ions. All right, so that's a fairly straightforward question. All right, all the information you need is there. The reduction of water to hydrogen gas and OH minus ions. Okay, so is it balanced? No, it's not. So you have to balance it, and then you have to balance it electronically as well. So over here you've got a neutral covalent compound, and over here you've got a negative charge. So you're probably going to add some electrons on here. Okay, but that's quite straightforward. Write an ionic half equation for the oxidation of manganate 6 ions to manganate 7 ions. All right, so remember these manganate ions are compounds of manganese and oxygen. So you need to work out if you've got manganese in the oxidation state 6, how does it convert into the oxidation state 7? Now remember that oxidation is the loss of an electron or a loss of electrons, so that should give you a clue. All right, you know, the formula of the manganese ion doesn't necessarily need to change. It could just be that the charge changes. Okay, and then once you've done that, you can have a go at putting them together to give you your overall equation. Okay, so it is worth remembering, okay, that here it's asking you the conversion of potassium manganate 6, whereas your ionic equation is just for the manganate 6 ion. All right, so if I go back and give you another example of this, all right, so if we look at MnO4 minus. All right, so oxygen is -2. So here, manganese is in the +7 oxidation state. So this is actually, this is, what's it called? Manganate. Yeah, this is a manganate 7 ion. All right, which might help you with the question you're working on at the moment. Which means that if I was to have potassium manganate 7, that would be KMnO4. Right. So, all right, that might help you with this here. Obviously, what I've just written down is potassium manganate 7. Okay, so but you should be able to work out what it is for potassium manganate 6 as well. Right. Okay. Moving on. All right. So pause it there, have a go at those questions, see how you get on. Aqueous solutions of potassium manganate 6 are only stable at high pH. At neutral pH, the substance disproportionates. The reduction product is manganese 4 oxide. All right. Write a balanced equation for this disproportionation reaction. All right. So obviously, disproportionation is the simultaneous oxidation and reduction. Okay, and it's the disproportionation of manganate 6. All right, so it's gonna go from manganate 6 to manganate 7, which is what we've done up here. So this, whatever you've got for this, that's going to be one of your products. Okay, plus the manganese 4 oxide. Now look, this is manganese 4 oxide. Okay, so what that means is, because it's manganese and not manganate, all right, it means it's not an ion. All right, and so your manganese 4 oxide, I think, did we have, I thought we might have seen it before, but no, we haven't. All right, but it should be fairly easy. Oh no, look, yeah, down here. Yeah, your manganese 4 oxide. Okay, so it should be fairly obvious what what the formula for manganese 4 oxide is. Okay, so so if you just, how are you going to get those two products? Bearing in mind that we're talking about aqueous solutions. All right, so it's probably going to be your manganate 6 plus some water. Okay, right, next. So if we move on, we've got now this interesting question, okay, where we have to use this formula, which is actually known as the, I don't think it specifies it here, it's known as the Lambert Law, if you'd like to look that up. Lambert Law, and basically it just means that, I mean, you can read it and you can see what it means, but if you think about, if you're having, say, not a cup of tea, maybe a cup of coffee, and at the bottom of your mug, there's a pattern on the bottom of the mug. Now, if you have a full cup of coffee, you can't see the pattern at the bottom of the mug. All right, but then as you drink more coffee and you get right down to the bottom, you might be able to see the pattern on the bottom of the mug through the remaining coffee. Okay, and that's because the amount of light that is absorbed is dependent on this E, which is specific to the particular substance, in this case the coffee, the concentration of the coffee. So if you have a really, really strong coffee, it'd be harder to see, but then also the length of the light that it passes through. Okay, so you can imagine if you've got your sample of coffee, if you've got this much coffee, and this is the pattern on the bottom, and you're looking at it like this, if that's the length, it's quite a large length, more of the light will be absorbed, so it'll be harder to see to the bottom of the mug. But once you get down to here, then not as much light will be observed and it'll be easier to see. All right, and that's essentially what this formula tells us. All right, so given the absorption A has no units and L is specified in centimeters, what are the units of the molar absorptivity E? Okay, so I think that should be fairly easy to work out. You've had a lot of practice of working out units from all the stuff on pressure. Okay, the graph on the right shows the absorbance of various solutions of potassium manganate at different concentrations. From this graph, calculate the value for the molar absorptivity of potassium manganate at 530 nanometers. So this is A, and this is concentration. Okay, and remember that A equals ECl. Right, and we want to work out what the absorptivity constant is. So the only other thing to remember is you need to really read the question carefully, because here we are told that the length is 1 centimeter. Okay, which means actually what we're dealing with is A equals EC. All right, so if I plot A against C, then E is the gradient. Okay, and you've had lots of practice of working out gradients from all the stuff we did about rates. Okay, so you can work out the absorptivity, and then you can move on to what is the absorbance of a solution whose concentration is. Now, this is where you need to be really careful, because we know that we've got our absorbance equals ECl, where L equals 1, all right, and E equals whatever answer we've got from part H. So the concentration, now we're given the concentration, so it should be easily just, the answer from this, multiply by this, multiply by 1. But we're in milligrams per decimeter cubed, so actually this question, it's not testing your ability to put numbers into this formula, it's testing your ability to convert this into moles per decimeter cubed, all right? And you know the relationship between moles and grams, moles and mass, so you can work that out easily as long as you remember to first convert this into grams. Okay. Assuming that the absorbance of the water was 0.4, calculate the concentration of potassium manganate in the tap water. So this is essentially the same as the previous question, except now we're going in the opposite direction. So rather than being given the concentration and you have to work out the absorptivity, now you're given the absorptivity and you have to work out the concentration. So it's the same process, but we need it again in milligrams per decimeter cubed. So we can do it's going to be 0.4 equals E, your answer from part H, times C times 1. And you work out C, but remember C will be in moles per decimeter cubed, and you need to convert the moles per decimeter cubed into milligrams. And just think, well, how would I convert moles into milligrams? You can easily convert moles into grams by using the molar mass, and then you convert grams into milligrams by try dividing by 1,000. Right. So, assuming that the toxic dose of potassium manganate 7 is 1 gram per kilogram of body weight, what volume of contaminated tap water would a 75 kilogram on-away resident have to drink to consume a toxic dose? So, if you think about this for a little bit, we know that the toxic dose is 1 gram per kilogram. And we've got 75 kilograms, so the toxic dose for a person would be 75 grams. And you've worked out in the previous question, in the water, how many milligrams per litre there are. Okay, so this is going to actually be 75,000 milligrams. And I know how many milligrams there are in 1 litre, so how many litres do I need to drink to get 75,000 milligrams? Right? Probably going to be quite a lot. Okay, right, but moving on to the final section. Reactions of potassium permanganate. So, KMnO4 reacts with concentrated sulfuric acid under carefully controlled conditions to form manganese-containing species compound X with that much manganese, that much oxygen. Mass spec, easy, no problem there. It's only got 2 things in it, that should take you 2 minutes. Hence, write a balanced equation for the reaction of KMnO4 with concentrated sulfuric acid. Okay, also should be very easy. Okay, you're going to have this thing plus this thing gives you this thing, all right, which has only got manganese and oxygen in. So where's the potassium going to go? Where's that potassium going to go? Well, I don't know. could be something to do with this. All right, so that should be a good clue there. All right. Good. All right, and suggest a structure for a molecule of compound X. All right. So we learned in the previous part that these compounds of manganese and oxygen are covalently bonded. All right. So just have a go at that. I mean, for these ones, you just got to just have a go. All right. I mean, as long as you have a good, you have a good go at it, and then check your answer. It doesn't matter too much if you don't get it. Some of these can be quite tricky. Okay. Compound X decomposes explosively to give MnO2 and O2 as the sole products. So again, we've got delta FH. All right. So we've got X gives us MnO2 plus O2. Now, obviously, depending on what X is, you need to balance this equation. All right. And then here we've got, I know that this has only got manganese and oxygen in, so it's going to be Mn plus O2. All right. So remember, that will need to be balanced as well. And then from that cycle, you can work out the value that you need to work out. All right. Which is this one here. Okay. Or alternatively, you can always do it, because remember we did Hess's law is crap, so it's combustion, it's reactants minus products, but if it's formation, it's going to be products minus reactants. All right, it's up to you. Okay, so really all this is it's a test of your actually I think it's quite a straightforward question, because you've already got so you need to have the balanced equation. You need to get this equation, you need to balance that. So in order to get this question right, you need to balance the equation, which is your compound X converting into manganese oxide and oxygen. All right. Right. Then we come down to the last two. Okay. So the overall yield of this reaction is typically 77%. Okay. So we're making heptanoic acid. So the yield of this, that's 77%. Okay, assuming this is the case and that a 10% excess of KMNO4 is used in synthesis, what mass of KMNO4 do we need? All right, so this is just a percentage yield question. So you need to think to yourself, well, if I want to get a mass of 300 grams from a 70% yield, all right, how many would I need to plan to make? How many moles would I need to plan to make if I'm only going to get 77% yield? Yeah. So if you think about it like this, so let's say if you were to get a 50% yield of this, you need to plan to make twice as many. Yeah. If you need 100 moles of this, but you only get a 50% yield, then you need to plan to make 200 moles of this. All right. So that's what you're doing. So you need to plan to make enough so that a 77% yield will give you 300 grams. Remember, we're working in moles though. So a 70% yield will give you the number of moles in 300 grams. Then you can work out the number of moles of this, and then from that you need to multiply it by 1.1 to get your 10% excess. All right, so that's just, it's all stuff that you know how to do. Yeah, it's all just working out moles and relationships between moles, but they just, they ask it in a very, in a bit of a more complicated way and with things that you're not really used to seeing, but it's still the same stuff. Okay, and then we have this question of, instead of using potassium manganate, we could use sodium. All right, so this sodium one, okay, and calculate how many times more expensive it would be to carry out the oxidation of heptanal using sodium, NaMnO4, rather than potassium. Okay, now I had a look at this question. Okay, it's fairly straightforward because you've got the price of 1 kilogram of potassium permanganate, but then you get this, 500 milliliters, 40% by mass. Okay, so what that means is, if I've got NaMnO4, right? It's £67.80 for 40% biomass of 500 millilitres. All right, so how much is that? Well, 40% biomass of 500 millilitres is 200 grams. Okay, so £67.8 is 200 grams. So from that, you can multiply it by 5 to get 1 kilogram. Okay, but the problem is that 1 kilogram of sodium permanganate and 1 kilogram of potassium permanganate contain different numbers of moles of manganate ions. So what you really need to do is, the most effective way to work this out is, because remember it's a molar relationship, not a mass relationship in your chemical reaction, like any chemical reaction. It will be most effective for you to work out what is the price per mole for both. All right, so work out for both of them price per mole. All right, now that's the end of that question. Okay, so I mean, these are difficult questions. Okay, not many people do this exam, and if it was easy, everyone would do it and everyone would get the top marks. But it's supposed to be difficult. Don't worry about not getting everything right. What I've tried to do is to show you that hopefully you can see that all the questions are doable. This isn't stuff that you have, it's not asking you sort of, final year degree level chemistry and expecting you to know it. It's all related to stuff that you've seen before, okay? But it does just take a little bit of thinking about. So rather than, when you go into a chemistry exam for your A-level, when you see a question and you think, oh, I know exactly what to write for that, this is not going to be like that. You do have to think a bit about it and just try and get something down. All right. So I hope that was useful. Good luck for tomorrow.